see the spectral series of a hydrogen atom, we'll see, right? So now we'll see here. Right. So in the last class, we have calculated like a total energy, all those things we have calculated. Now we'll see the frequency of the emitted radiations in this what we call Bohr's theory here. So frequency of the emitted radiations. Frequency of the emitted radiations. Can calculate. Okay. So generally, the frequency of the emitted radiations can be found by the using the relation like E is equals to h nu, which is En2 minus En1. So here we write E is equals to h nu, so which will be equals to En2 minus En1 here. Okay. So here E is N2 is nothing but the energy which is corresponding in the N2 level, and E N1 is nothing but the energy which is corresponding to in another level. So therefore, we write the value of E N2. So E N2 is nothing but its value is equals to minus M e power 4 by 8 epsilon naught square. Yesterday I have written this epsilon naught as k naught we have written. Now we are writing it as epsilon naught square. So it will be h square and n2 square. And similarly, minus en1, we'll write here value as m e power 4 divided by 8 epsilon naught square h square, and it is n1 energy level, so it will be n1 square we can write. Therefore, we can write this h nu, which will be equals to h nu, which will be equals to. So if I take this m e power 4 by 8 epsilon naught square h square as outside, if I take, so the remaining here will be 1 by n1 square minus 1 by n2 square we have. Okay, so from this relation, we'll take m e power 4 by 8 epsilon naught square. This is epsilon naught square outside and h square outside. If you take, we'll be remaining with 1 by n1 square minus 1 by n2 square. Okay, suppose after this, if you consider c is the velocity of light. Okay, c is nothing but the velocity of light. So we'll take c is the velocity of light, and similarly, lambda is nothing but the wavelength. So therefore, we have a relation between this c and the lambda, which we'll be calling it as a nu is equals to c by lambda relation is there. Okay. So therefore, here in this h nu, in place of nu, we'll substitute this c by lambda. Therefore, it will be c by lambda. So which will becomes now the above equation becomes c by lambda is equals to m e power 4 by 8 epsilon naught square, and it will become h cube because that h we have taken into the denominator. So it becomes h cube into 1 by n1 square minus 1 by n2 square. Okay, so we have got c by lambda is equal to this we have. So now after this, so here we'll write here. So continuation here I'm writing. So now if I write this as 1 by lambda, so which will be is equals to m e power 4 by will become 8 epsilon naught square h cube c into 1 by n1 square minus 1 by n2 square we have. Right. So this we can write it as a 1 by lambda, which will be equals to, and this entire value of me power 4 and 8 epsilon naught square h cube c, which is known as a Rydberg constant R. So R into 1 by n1 square minus 1 by n2 square will get. Okay, 1 by lambda is equals to R into 1 by n1 square minus n2 square you are going to get, because R value is nothing but that is equals to me power 4 8 epsilon naught square h cube c, whichever we have this one. So this is nothing but the Rydberg constant, and we know the Rydberg constant value R, that is equals to 10.97 into 10 to the power of 6 m minus 1. Okay, so this is what Rydberg constant we have. So therefore, 1 by lambda, which is nothing but the reciprocal of wavelength, we will be calling it as a wave number, which we can represent as a nu bar. So which will be equals to 1 by lambda, which is nothing but R into this what we call 1 by n1 square minus 1 by n2 square here we have. Okay. So this equation, whichever we have got, like a nu bar is equals to 1 by lambda is equals to 1 R into 1 by n1 square minus 1 by n2 square. So this is the equation or expression for the wave number of radiation emitted by the electron when it is jumping from n2 orbit to n1 orbit. That is nothing but n2 is a higher energy level which we have. So this is the higher one which we have, and n1 is nothing but the lower orbit here. Okay, so the amount of radiation which is emitted when the electron is jumping from N2 level to N1, that is N2 orbital, which is nothing but higher orbital, to the lower orbital N1. So this is the amount of radiation which is emitting out. Okay, so this is what we have. Okay. So next, after this amount of radiation which has been emitted, we can uh, know the different electron energy levels in hydrogen atom. Okay, different what we call electron energy levels. Electron energy levels. Electron energy levels in hydrogen atom. Hydrogen atom. We'll see different electron energy levels in case of hydrogen atom here. Okay. So the orbital energy of an electron, which is revolving in orbit, that is nothing but suppose this is the nucleus which we have. Around that we will be having the what we call orbitals. Around this we will be having the orbitals in circular shape as accordingly to the Bohr's theory. So electron may be revolving in the first orbital or second orbital, like we may be having the n orbitals if we are having. Say that the orbital energy of an electron revolving in nth orbit. Suppose in nth orbit means it may be n may be 1 or 2, whatever it may be. So already we have seen that energy level nth orbital En is equals to, we have a formula like me power 4 by 8 epsilon naught square n square h square. So this is the orbital energy of electron revolving in the nth orbit. Here we have 8 epsilon naught square n square. So if n is equals to 1, say that if it is first orbital, then we can substitute n is equals to 1. If it is second orbital, n is equals to 2, like that. If it is a third orbital, it depends. Okay. So now here, by taking the mass of the electron here, mass of the electron, we know that 9.11 into 10 to the power of minus 31. And the charge of the electron is 1.6 into 10 to the power of minus 19. And here 8 is constant. And epsilon naught value already we know that is 8.854 into 10 to the power of minus 12. And similarly, H value, that is the Planck's constant, like a 6.62 into 10 to the power of minus 34. And taking all the values and by substituting all the values here, we will be getting like what we call here value, we are going to get minus 13.6 divided by n square. And this is energy is in terms of electron volts we have. Okay, in terms of electron volts. So the electron energy level En, what we are getting, En is equals to minus 13.6 by n square electron volts we are going to be get. Okay, electron volts we are going to be get here. So like that, here if you substitute uh, in this equation, whatever we have got, En is equals to minus 13.6 by n square electron volts, whichever we have got. So in this equation, if the electron is here minus sign, why we have got this minus sign is the electron is bound to the nucleus by attractive force. The sign which we have got minus here is due to the electron is bound to the nucleus by attracting force or attractive force here. And to separate the electron from the nucleus, that means it is bounded to the nucleus. So if you want to separate the electron from the nucleus, the energy must be applied to it so that it will be coming out from that orbital. Okay. So giving different values to the n here, we can calculate the orbital energy, or we can say that binding energy. Why we are calling binding energy is here as it is getting negative sign which is bounded to the nucleus. So by giving the values of n for different orbitals, so we will be getting this orbital energy or binding energy of the electron in different orbits we are going to be get here. Okay. So suppose, so if you see here, the value of En for different what we call for different levels. Like suppose if you take first energy level, which is E1, we are going to become, that is nothing but n value we are substituting simply 1 here in this case. Here in this case, we are going to be substitute here n value is equals to 1. So we are going to get E1 is equals to same as minus 13.6 electron volts we are going to get. E1 value is equals to minus 13.6 electron volts we are going to get. So here what we have substituted is actually when the value of n is equals to how much here? 1. N is equals to 1 here. So if n is equals to 1, the level which we call it as a, if we will be calling it as a K shell we are going to be calling. We will be calling it as what? K shell. So E1 is equals to minus 13.6 electron volts. When n is equals to 1, if you substituted, we have got here. Similarly, if you want to get calculated for the second orbital, so it is E2. So n value we have to substitute 2. So n square becomes 4. So minus 13.6 by 4 if you calculate, we will be getting it as a minus 3.4 electron volts you are going to get. So that is nothing but here n is equals to how much we have substituted, n is equals to 2 we have substituted. So we will be calling this as L shell we are going to be called. We will be calling it as what? L shell we are going to become. So similarly, if you want to get the energy, orbital energy of the third level, so we call it as a E3. So simply n value 3, if you substitute, it will be 3 square 9 minus 13.6 by 9 if you do, you are going to get minus 1.51 electron volts you are going to get. So here this n value is how much we have taken when n is equals to 3 here. And this shell, we will be calling it as a M shell we are going to become. We will be calling it as what? M shell we are going to become. So on, if you substitute different values of n, you will be getting what we call different energy levels we are going to get here. Okay, that is the orbital energy you are going to get. So that means if you substitute 4, it will become 16 minus 13.6 by 16. If you do, you'll get certain value. Okay. So if it goes on substituting, so say that infinite energy level, if you want to calculate the orbital energy of the infinite, so it will be equals to 0 electron volts you are going to be getting. You will be getting it as a 0 electron volts because n value is infinite. So this is a limiting case which we have. So now we shall consider the energy level diagram, so which can be drawn in terms of what we call various electron orbits to the scale of their radii, but it is uh, we have to represent in what we call horizontal energy scale. Okay, so like that means actually, so if you see in terms of what we call circular orbit, so if this is the nucleus if you are having, so around that the orbital energy for n is equals to 1 if you consider. So as we have taken, we have got it as a minus 13.6 electron volts we have got. So suppose similarly, if you take for second orbital here, so for n is equals to 2. So for this we have got minus 3 point the what we call 3-4 electron volts we have got for n is equals to 2. So this is for n is equals to 1, and this is n is equals to 2, and similarly for n is equals to 3, we have got minus 1.5 electron volts. So this, instead of showing this in terms of what we call circular orbits, we can give in terms of energy levels we can give here. So the innermost energy level, whichever we have, this is a minus 13.6 electron volts required. So when n is equals to 1 we have. And then for another one energy level, so its value is minus 3.4 electron volts. So energy level diagram for n is equals to 2 here. And next one is state we'll draw here. Next one, it will be minus 1.57 electron volt for n is equals to 3 here. So like this, if it goes on substituting, so we'll be getting different energy levels. So generally this the distance from here to here it is more, and there later on the distance will be very less. So this is the what we call representation of energy levels for hydrogen atoms here. Okay. So if you see about this energy level diagram, so we can come across what we call some points here. So when a hydrogen atom receives a photon energy which is greater than the binding energy, that is nothing but, for example, if you see this for first orbital, the binding energy is 13.6 electron volts. Okay, so greater than its binding energy, which is nothing but 13.6 electron volts. So it absorbs the photon, and electron of the atom passes from its discrete ground state to a continuous state. So let the electron absorbs 25 electron volts, suppose if you say. This energy is not only sufficient to remove the electron from the atom, but it imparts energy that is nothing but 25 electron volts minus 13.6 electron volts, which is equal to 11.4 electron volts. That is nothing but the minimum amount of energy which is required in order to remove the electron from the first orbital is 13.6 electron volts. So if you are absorbing more than that, so then the 25, suppose say that if it is 25 electron volts, so 25 electron volts minus 13.6, which is 11.4 electron volts uh, energy it is going to be absorbed. Okay, so this is what we have. So like this, similarly, if the electron absorbs an energy 13.6 electron volts, the electron is to raise from this to n is equals to infinite. Okay, so let the electron absorbs an amount of energy 13.6 electron volts. Okay, the electron is raised to n is equals to infinite level. That is, the electron is free from the nucleus, and it has only its what we call thermal kinetic energy here. So since the electron is completely removed from the what we call atom, the atom is said to be ionized. The atom is said to be ionized. So the energy of 13.6 electron volts is called ionization energy of the atom. We are going to be called. Okay, the 13.6 electron volts is called the as ionization energy of the hydrogen atom. We can call. So in this way, the ionization potential of the hydrogen atom is 13.6 electron volts we have. Okay. Suppose if I say that the electron in this orbital absorbs, say that a energy of some 10.2 electron volts, suppose if it is absorbing. Okay. Suppose this electron which is in this orbital, if it is absorbing a energy of 10.2 electron volts, if it is absorbing, as it is obvious from the energy level diagram that the energy is equals to the difference of the two states, that is the energy state 2 and energy state 1 here, energy state 2 to 1 here. So hence the electron is excited from the n is equals to 1 to n is equals to 2 states. That is nothing but actually here is 10.2 electron volts, 10.2 electron volts. How we are getting is the difference between these two, 13.6 electron volts and this 3.4 electron volts. So the difference is here it is 6 minus 4, 2, and this is a 3 minus 3, 0, and this is 1 here. So 10.2 electron volts we are going to get. That means if the electron is absorbing 10.2 electron volts energy, if it is absorbing, then automatically what will happen means it is going to be, that is nothing but the electron is going to be excited from n is equals to 1 to n is equals to 2 here. Okay, this is nothing but n is equals to 2, n is equals to 1 state, and this is nothing but n is equals to 2. So by absorbing 10.2 electron volts, it is going to be excited from this state to this state. So if I see in this diagram like this, so n is equals to 1 state if you are having, n is equals to 2 state. So by absorbing 10.2 electron volts, so this electron is going to be excited into the second energy level here. Okay. So like this, we can calculate the amount of excitation energy for what we call whenever the electron is jumping from one energy level to another energy level. Suppose if you want to calculate the what we call the excitation energy in order to jump, otherwise in order to excite the electron from state 1 to what we call state 4, that is nothing but first energy level to the fourth energy level. If you want to excite, then how much energy it is required. Okay, so here as we know that in the first energy level it is 13.6 electron volts it is having, and in the fourth energy level it is having how much is 0.85 electron volts is there. So the difference here it is what we are going to get is how much here? 2 here, 12.75 electron volts. So if the electron is absorbing 12.75 electron volts of energy, if it is absorbing, so automatically here the electron is excited to, like if it n is equals to 1, n is equals to 2 here, n is equals to 3 here, n is equals to 4 here. So the electron is going to be excited from first energy level to fourth energy level. How it is exciting? It is absorbing energy of 12.75 electron volts. It is absorbing and it is jumping from first energy level to fourth energy level. It is jumping. So like this, the excitation of the electron from one orbital to one energy level to another energy level, it is going to be happen here. So this is what explained in the case of the what we call a Bohr's atomic model. It has been explained. Okay. Now we'll see the what we call a spectral series of hydrogen atom. Okay. What is spectral series of hydrogen atom and how it is going to be takes place here? We'll see here. Right. So spectral spectral series of hydrogen atom. Spectral series of hydrogen atom. Okay. Right. So it has shown that the energy of outer orbit is greater than the energy of the inner ones here. Okay, it has been shown that the energy of the outer orbit is greater than the energy of the inner orbits. So when the hydrogen atom is subjected to some external energy, the electron jumps from lower energy state to higher energy state. So this is the lower energy state of, suppose if it is having, so it is a higher energy state. So what will happen when the hydrogen atom is subject to some external energy, the electron jumps from lower energy state to higher energy state. Like this, it is going to be jump from lower energy state to higher energy state. That is nothing but the hydrogen atom is excited. The hydrogen atom is excited. So the excited state is not stable. That means it has been jumped from lower energy level to higher energy level. And this is what we calling it as the excited state we are going to be called. And this excited state is not stable. Hence, the electron, again, it returns to its ground state within the 10 to the power of from here to here. It is going to be jumps back from higher energy state to lower energy state within the fraction of seconds. That is nothing but 10 to the power of minus 8 seconds. Within the 10 to the power of minus 8 seconds, the electron, whichever it has been excited from lower state to higher state, and it will be coming back to the ground state within this 10 to the power of minus 8 seconds. It is going to be come back here. Okay. So the excess of energy is now radiated in the form of radiations of different wavelengths here. Okay. So the different wavelengths consisting of spectral lines here. So what we are saying here, so the electron, whichever it is in the lower energy state, by absorbing certain amount of energy, otherwise, if you are subjected, suppose this hydrogen atom, it is there, if this hydrogen atom is subjected to some external energy, the electron in the lower energy state is going to be jump into the higher energy state. And that is nothing but we'll be calling it as a hydrogen atom is excited, we are going to be calling. So then after what will happen means the electron will not be stays back in the higher energy state, but it will be coming back to the ground state within this time 10 to the power of minus 8 seconds. Okay. Within the 10 to the power of minus 8 seconds. So whenever it is coming back to the ground state, whatever may be the amount of excess energy which is absorbed by this hydrogen atom, the energy which is absorbed by this hydrogen atom, so that energy is going to be radiated when it is jumping back from a higher energy level to lower energy level. So whenever it is jumping from higher energy level to lower energy level, so it is going to be radiates the energy in the form of what we call some radiation or light, whatever it may be. So it is going to be radiates this energy of different wavelengths. It is going to be radiates here. So the different wavelengths consisting of what we call these different wavelengths, they are going to be constitutes what we call a spectral series we are going to be calling. This we will be calling it as what? Spectral series. So which is which are characteristic of atom which is emitting them. Okay. So here what we are saying, when the hydrogen atom is subjected to some external energy, it will be going from lower energy state to higher energy state, and it will not stay back there for a complete time, but it will be coming back to the ground state within 10 to the power of minus 8 seconds. Okay, it is coming back to the ground state within the 10 to the power of minus 8 seconds. So whenever it is coming back to the ground state, the excess energy, whichever it has been absorbed by the hydrogen atom, it will be emitted in the form of a radiation of different wavelengths. And these different wavelengths, we are going to be called it as what? Spectral series we are going to be called. And as we are studying about the hydrogen atom, we'll be calling it as a spectral series of this hydrogen atom we are going to be called here. Okay. So now the wavelengths of different numbers of the series can be found, the wavelengths of the different what we call radiation, whichever we have. So we can found with the help of this equation, which is already we have seen nu bar is equals to 1 by lambda, which is equals to R into R is nothing but Rydberg constant into 1 by N1 square minus 1 by N2 square. 1 by N1 square minus 1 by N2 square here. Right. So now we'll see what type of spectral series we are going to be get in this case. So the first spectral series which we are going to be get here is a Lyman series we call. We call it as what? Lyman series. We call it as what? Lyman series here. So this Lyman series, whichever we have, so this series consisting of all the wavelengths which are emitted when an electron jumps from an outer orbit to the first orbit, an outer orbit to the first orbit. So that means here uh, it is jumping from outer orbit to the first orbit. First orbit is nothing but n1 is equals to 1 we are going to be have. N1 is equals to 1 we are going to be have. So N2, that is nothing but the outer orbit. It may be like a second orbit or third orbit or fourth orbit or infinite orbit. That means if the electron is jumping from 4 to 1, the series whichever we are going to be call it as a Lyman series, or 3 to 1 or 2 to 1 or infinite to 1, whatever it may be, we will be calling it as what we call Lyman series we are going to be called. So N1 is equals to 1 is nothing but what? It is a k orbital. It is a k orbital we are going to become. So for this case, if you calculate how much wavelength here you are going to get here. So N1 is equals to how much we have? N1 is equals to 1. Suppose N2 is equals to 2 if you are having. Say that the electron is jumping from 2 to 1 if it is jumping. Then automatically by using this equation, 1 by lambda is equals to R into 1 by N1 value is 1, 1 square minus 1 by N2 value is 2, 2 square here we have. So this is going to be like if you take the LCM and all those things, you are going to get it as a 3R by 4 you are going to get. 3R by 4 you are going to get. That means lambda is equals to 4 by 3R you are going to get. Lambda is equals to 4 by 3R. So here by substituting the R value, that is nothing but the Rydberg constant value 10.97 into 10 to the power 6. If you substitute, we are going to get around like a 1216 into 10 to the power of minus 10 meters you are going to get 10 to the power of minus 10 meters. That is nothing but we call it as a 1216 angstroms we are going to become. So the lambda, the wavelength of that one will be equals to 1216 angstroms you are going to get. Okay. So here, when the electron is jumping from second energy level to first energy level, the series, whichever, the spectral series, whichever it is produced, it is having the wavelength of 1216 angstroms it is having. Similarly, we can calculate whenever it is jumping from what we call N1 is equals to 1, it has to become to the lower energy level, like N2 is equals to 3 if you are having. That means the electron is jumping from third energy level to first energy level. If it is jumping, then we will get the wavelength for this one is lambda is equals to like 1026 angstroms you are going to get. 1026 angstroms you are going to get. So similarly, you can calculate whenever it is jumping from higher energy level to like n is equals to 4, n2 is equals to 4 to 1, or n2 is equals to 5 to 1, like that you are going to get different what we call radiations of wavelengths you are going to get. Okay. So the radiations wavelengths you are going to calculate. Suppose if it is jumping from higher energy, last energy level, which we will be calling it as a limiting case, we are going to be a limiting number. That means n1 is equals to 1. This n2 should be infinite. So here we'll substitute n1 value 1 and n2 is equals to infinite. If you substitute, we are going to get this lambda is equals to simply 1 by r you are going to get. So this, if you calculate lambda is equals to 912 angstroms you are going to get. Calculate this, you are going to get 912 angstroms you are going to get. That means the series of wavelengths lies whichever we have like a 912 or a 1216, whatever it may be. So this belongs to the what we call UV region, which we call it as a ultraviolet region we are going to become. The series of wavelengths, whichever it is, in the case of the Lyman series, belongs to the UV series we have. So this is about the Lyman series. That means whenever the electron is jumping from higher energy level to the first energy level, so we call it as a Lyman series, and those radiations belongs to the UV region. And then next we will get another type of series whenever it is jumping the electron from one energy level to another energy level, which we call it as a Balmer series, BALMER, Balmer series we are going to define. Balmer series here. Okay. So in this case, Balmer series, this series consisting of all the wavelengths which are emitted when electron jumps from an outer orbital to the second orbit, outer orbital to the second orbit. That is nothing but N1 value should be 2 and N2 value should be 3 or more than that one, 3, 4, 5, and so on up to infinite. That means if 3 to 2, if it is jumping, we can call it as a Balmer series, or 4 to 5 also we call it as a 4 to 2 also we call, and similarly 5 to 2 also we can call. Means the electron should be in third orbital or fourth orbital or fifth or and so on. It has to jump from there to second orbital, 3 to 2 or 4 to 2, whatever it may be. The series, whichever we are going to be arise, we call it as a Balmer series we are going to be called here. So for this Balmer series also, we can calculate the wavelengths of different members we can calculate. So here if you take first number in this case, first one. So here N1 should be 2 and N2 should be 3 you should have. N2 should be 3 have. So therefore again by using the formula 1 by lambda is equals to R into 1 by 2 square here minus 1 by 3 square. So if you calculate this, you are going to get it as a 5R by 36 you are going to get. 5R by 36 you are going to get. So from this, we can calculate lambda. Lambda is equals to 36 by 5R you'll get. Lambda is equals to 36 by 5R here. So by substituting R value, that is a Rydberg constant, that is a 10.97 into 10 to the power of 6. So we will be getting the wavelength as 4861 into 10 to the power of minus 10 meters you'll get. Otherwise, we can it as a lambda is equals to 4861 angstroms you are going to recall. 61 angstrom. That means whenever it is coming from n is equals to 3 to n is equals to 2 here, whenever it is jumping from here to here, so it will radiate the energy which is having the wavelength of 4861 angstroms you are going to get here. Understand? So second case, if you see, here we calculate the second case. N1 should be 2 you should have. N2 should be more than this 3. 4 if you take. N2 is equals to 4 if you take. So similarly, by substituting the values of this, 1 by lambda is equals to R into 1 by 2 square minus 1 by 4 square. So which we are going to get it as in this case is 3R by 16 you are going to get. 3R by 16. That means the lambda value, whichever you are going to get, is 16 by 3R you are getting. R value is nothing but the Rydberg constant. So if you substitute, you are going to get this lambda value as 3646 angstroms you are going to get. 3646 angstroms you are going to be get here. Okay. So in this case, that means the electron is jumping from in this n is equals to 4 to n is equals to 2 here it is jumping. So whenever it is jumping from here to here to here, it will radiates the energy, radiates the what we call light, which is having the wavelength of 3646 angstroms it is going to be. So like this, we can calculate what we call different energy levels whenever it is jumping from n is equals to 5 to 2 or 6 to 2 or 7 to 2 or maybe. Finally, if you take the limiting case, N1 should be 2 and N2 should be infinite you should have. N2 should be infinite you should have. So in this case, if we calculate, we get 1 by lambda is equals to R into 1 by 4 minus 1 by infinite, you are going to get simply, we get it as R by 4 you are going to get. That means lambda is equals to 4 by R you are going to get here. So if you substitute the Rydberg constant, in this case, we getting it as a 3646 angstroms you are going to. Okay. So 3646. Sorry, here I have written wrong. This is not a 3646. So this is like a 4861 angstroms. 4861 angstroms. So here 3646. So that means final whatever it may be from higher energy state to this state, n is equals to 2 state, and here n is equals to infinite whenever it is jumping. So you are going to get this radiation, 3646 radiation you are going to get. So this is what we call it as a Balmer series. So all these wavelengths, whatever we have got, like initially 4861 we have got, and finally we have got what we call 3646 angstroms we have got. So in between this radiation, whichever we are going to be get, so this is also belongs to what we call invisible and near ultraviolet region you are going to get. So this Balmer series, whatever it may be getting, this is in between visible and near ultraviolet region you have. Okay, so this is what we call it as a Balmer series. Next one, we have like a fashion series. Okay, next one is a fashion series. Okay, fashion series. So in this case, the electron jumps to m orbit. That is nothing but n1 is equals to 3, and n2 should be equals to 4, 5, 6, and so on up to infinite. Up to infinite, you are going to be happy. So in this case, whenever electron is jumping from this higher energy level to m orbit, that is nothing but that n1 is equals to 3, then we whatever may be the radiation, like suppose if we are not calculating for each and every one here, and each orbit we are not, n1 is equals to 3, and this n2 may be like what we call 4, 5, 6, 7, or finally like this, if it goes on infinite value. So whether it is jumping from 4 to 3, or 5 to 3, or 6 to 3, or 7 to 3, or from here to here, infinite value to here. So the radiations, whatever it may be getting of different wavelengths here, whenever it is jumping. So here you are going to get like this. So here you are getting. So this we will be calling it as what the spectral series, we will be calling it as a passion series we are going to be called. So this generally the radiation which we are going to get belongs to this IR region. Okay, the wave numbers whichever we are going to get is IR region. That is nothing but infrared region we are going to be called here. Okay, infrared region. So next one, after this, we have like a what we call a bracket series. Okay, so bracket series, bracket series. So in this case, what we call electron jumps from outer orbit to the fourth orbit. That is nothing but the electron jumps to n orbit. Okay, electron jumps to n orbit. So electron jumps into an orbit means n1 should be equals to 4, and n2, and n2 should be more than this 4. It should be 5, 6, 7, and so on up to infinite. So this one we will be calling it as a bracket series we are going to be called here. So the lowest level in the case of the bracket series, n1 is equals to 4, and higher levels may be 5, 6, 7, and so on. So like this we have, and up to infinite if we take lower should be n1 is equals to 4. Whether it is jumping from here to here, or 6 to 4, or 7 to 4, or so on infinite if we take. So it is going to be radiates energy here. So it is going to be radiates energy, right, in this form. And these wavelengths, generally in the case of the bracket series, they are going to be infrared region. of the spectrum you are going to be on. So these also comes under the bracket series, also comes under the what we call infrared region we have. And next one, we call it as a fund series, PFUND fund series. So in this series, it consisting of all the wavelengths which are emitted when electron jumps from an outer orbit to the fifth orbit, that is nothing but O orbit, so which will be giving rise to this what we call fund series. You are going to be giving rise. Okay, it is going to giving rise the fund series. That means N1 should be equals to 5 here, and N2 value is equals to more than this 5, like 6, 7, 8, and so on we have. Okay. So whenever it is jumping from 6 to 5 or 7 to 5 or 8 to 5 or infinite to 5, whatever may be the emitted radiation which are having the wavelengths belongs to this fund series we are going to look at. So this also lies in the infrared region of the spectrum. Okay. So this is what we have, like a different spectral series we have whenever it is going to be jump from what we call from one energy level to another. So now we'll see the energy level diagram. So if you easily understand here, we represent the this what we call all these series. So initially, if we take the lowest energy level is n is equals to 1 we have. Then after this is okay, so let's extend this. So this is the lowest energy level, which is n is equals to 1. And above this, we have like a this n is equals to 2. Then we have a n is equals to 4. Sorry, n is equals to 3, this one. And then we have a n is sorry, n is equals to 4. It should be straight, but here I'm not getting to draw straight line. N is equals to next one. So n is equals to 5. And if it goes on do here, so final one, I'll take it as a continuously, it will goes on, n is equals to 6, 7, and so on. This one I'm taking it as n is equals to infinite and right. So when the electron, when we are going to get this Lyman series is when electron is jumping from second to 1 or third to 1, or when it is jumping from n is equals to 4 to 1, or it's jumping from like n is equals 5 to 1 or infinite, which we call it as a limiting series we call. Okay. So like this, whenever it's jumping, so this entire electron is jumping from n is equals to 1 or 2 to 1 or 3 to 1, 4 to 1 or like this, n is equals to 1. This one, n is equals to 2 to 1 is from n is equals to 2 to 1, we didn't run, no? It should be 1 line. N is equals 2 to 1, 3 to 1, or 4 to 1, 5 to 1, or infinite to 1. So this series, we call it as a Lyman series. Is a Lyman series, we can call it. So here, generally the electron energy of this one will be 13.6 electron volts. Next will be minus 3.4, and so on you are going to have. Suppose if the electron is jumping from n is equals to 3 to 2 here, otherwise 4 to 2 here, or from 5 to 2 or infinite value to 2 here. Okay, 3 to 2, 4 to what we call the 2 or 5 to 2 or infinite to 2 here. So this we will be calling it as what Balmer series we are going to call. We will be calling it as what? BLMBR Balmer series we can call. Right. So like this, we can draw the Paschen series. Paschen series is nothing but from 4 to 3 or 5 to 3 or infinite to 3, like this you can get. Okay. Paschen series is nothing but 4 to 3, 5 to 3 or infinite to 3. So this series we call it as a Paschen series, you can call it. This is a Paschen series. So similarly, we can get the bracket series, that is from 5 to 4 or infinite to 4. Paschen series we are going to get. And then after from infinite to 5, like this can continue. So this we will be calling it as a quant series. So this is bracket series. This is the quant series. We can call this is a bracket series. So this is what energy level diagram we can call here. So this is the energy level diagram. Okay. So these all are explained by what we call Bohr's theory here. So next, what actually the Bohr's theory limitations we have to see here. Now limitations in Bohr's theory are drawbacks of Bohr's theory, you can say that. Drawbacks of Bohr's theory here, we'll see here. So if you see the Bohr's theory, it was able to explain what we call successfully a number of experimental observed facts, and it is correctly predicted the spectral lines of neutral hydrogen atom. For hydrogen atom, it has been predicted correctly, experimentally done things. Okay, for hydrogen atom, and for a singly ionized helium atom. So Bohr's theory is successful for hydrogen atom, single or ionized what we call helium atom. Ionized helium atom. In these two cases, it has been successfully explained. But however, this Bohr's theory has some drawbacks, which does not explain some things. What are those? We'll see here. The first one is the theory could not account the spectra of atoms more complex than the hydrogen atom. Means it is limited to hydrogen atom only. For complex atoms, that means more than atomic number, if you have like 2, 3, 4, or 5, whatever it may be, for these atomic number atoms, the Bohr's theory does not explain the how the what we call a spectra is forming in these atoms. Didn't explain. So this is one of the failure of this Bohr's theory we have. And second one which we have is this theory, this Bohr's theory does not give any information regarding the distribution and arrangement of electron. Distribution and arrangement of electrons. Arrangement of electrons. So about the distribution and arrangement of the electrons, this theory does not explain properly. And third point, if you see, it does not explain the experimentally observed variations. Experimentally observed variations. Observed variations in intensity of the spectral lines in the what we call intensity of the spectral lines of an element. Okay, it does not explain the experimentally observed variation in intensity of the spectrals of the element. That is also failure of this what we call Bohr's theory we have. And one more failure which we have is this theory does not otherwise this theory cannot be used to calculate about the transition from one level to another, such as what we call such as the rate at which they occur or the selection rules which apply to them. Okay, So the selection rules means from where to where what we call this uh, transitions which are occurring from which orbital to which orbital or which energy level to which energy level it is happening, that is not explained by this Bohr's theory. This is also one of the drawback which we have. And this theory fails for accounting the fine structure of a spectral line. That is fine structure of spectral line. Fine structure of spectral line means actually it was found that when spectral lines emitted by an atom are examined, each line is composed of several lines